This is going to be section 8.4, video part 2. So I was saying here that if we let x equal the tangent of a, then the tangent of theta, or we let x equal a times the tangent of theta, I'm sorry I said that incorrectly, then the tangent of theta equals the ratio of x over a. So remember, tangent is opposite over adjacent. So that means that the length of the side opposite of theta is going to be x, and then the length of the adjacent side is going to be a. So in this case, if we solve, oops, spelling that wrong. If we solve for the hypotenuse side in this triangle, we're going to use the Pythagorean theorem again, giving us that expression, the square root of x squared plus a squared. Okay, so what we saw in the last example is that we not only have to make a substitution for x in terms of our trigonometric functions, but we also have to figure out then what this expression should be equivalent to with our trigonometric functions. So let's do a similar proof where we're starting with the length of that hypotenuse side, and we're going to go ahead and let x equal a times the tangent of theta. So we have a times the tangent of theta squared plus a squared. Let's continue to do some algebraic manipulation here. If we square that term, we'll get this expression. And then let's factor out that a squared from both terms. From here, let's once again recognize that we have a Pythagorean identity. Remember that the Pythagorean identity here says that tan squared plus 1 is equivalent to secant squared theta. So we have now shown that rather than writing the square root of x squared plus a squared, we can substitute that with this expression, which, if simplified, becomes a times the secant of theta. So to summarize case 2, what we're doing here is we're letting x equal a times the tangent of theta, and as a result, we're able to say that the square root of x squared plus a squared can be written as a times the secant of theta. So let's take a look at an example involving case number 2. So here, we're going to be doing a definite integral just to kind of show you how that process differs from the indefinite integral we used last time. But you're seeing that same setup where we have a rational function where the denominator is the square root of x squared plus a squared. And again, that's how we know that it's case 2, because of the format of the terms underneath that square root. So let's go through the same type of steps that I did in the last problem. Step 1, let's figure out what x and a should be. Step 2, let's find dx based on that information. Step 3, let's figure out what substitution we can make for that denominator. And then step 4, let's do the substitution and rewrite our integral. So what I think a good idea would be to do here is to go ahead and pause the video, try filling this stuff in, and see if you can get it. Okay, so if I'm identifying all of these things, then I should say that x, in case number 2, should be 4 times the tangent of theta, because in this problem a is 4. That means that dx equals 4 secant squared theta d theta, and also the substitution that I can make for the entire denominator is 4 secant theta. Putting all of that together, my dx can be replaced with the 4 secant squared theta d theta, and my denominator is 4 secant theta. So we're seeing some cancellation again, so that really we're just integrating the secant of theta d theta. Now, I don't know if anyone has already considered this, but this was a definite integral. So we do need to determine limits of integration here. And if we're integrating with respect to theta, then we may want to go ahead and change 0 and 1 into values that reflect theta. The other option is to find the antiderivative, turn it back into an expression of x, and then evaluate using 0 and 1. So it's completely up to you. You can try it either way. But let's say we go ahead and figure out those limits of integration. So first of all, I again need an expression, or not just an expression, but an equation that relates my x and my theta. And so x equals 4 tan theta is the perfect relationship to use. First of all, I know that the lower limit of integration is 0, and it's in terms of x at the moment. So let's take that equation, let x equal 0, and solve it for theta. If I divide by 4, I'm going to get 0. And if I do an inverse tangent of 0, I'm going to get 0. So my lower integration remains 0. Let's take a look at the upper limit of integration. This time, I'm going to let x equal 1. Kind of combining a few steps here. I know that my theta is going to be the inverse tangent of 1/4. There is no nice angle on the unit circle that produces that ratio of 1/4 when it comes to sine and cosine values. So this is actually going to be some decimal expression, but the better way to go is just to leave it as the inverse tangent of 1/4. So if we can't calculate it using the unit circle, we can just write it that way. Okay, so we've got everything. We've got an entirely new integral that no longer has x's. Instead, it has trig functions involving thetas. Let's go ahead and find our antiderivative, and let's evaluate it over our new integral. One thing to note here is that the antiderivative of secant, just in general, is not one that's easy or obvious. If it were secant squared, that'd be nice, because we know it would be tangent. But there is a formula that the book provides that tells you exactly what the antiderivative of secant theta is. And it is the natural log of the absolute value of the secant of theta plus the tangent of theta, and then obviously plus c when we're talking about the general or indefinite form. So we are going to be using that here. So we're going to get the natural log of that same secant theta plus tan theta in absolute value form, but we're going to want to evaluate it over this interval. So let's start by plugging the inverse tan of 1/4 in for both of my thetas. So notice here I've got the secant of theta, where theta is this inverse tangent expression. And then I've got the tangent of theta, where again theta is that inverse tan expression. Okay, so that is the first expression. The second expression is going to be the natural log of, I'm kind of running out of room here, but we're going to have the secant of theta, plugging in 0, the secant of 0 plus the tangent of 0. Alright, I need a little bit more paper here to go ahead and continue simplifying all of this. So let's do that. Alright, so back to what we have here. We've got 4 different expressions that need to be evaluated in order to simplify our answer here. I'm just going to rewrite all of it in one line. Okay. So again, 4 things that need to be evaluated. 1, 2, 3, 4. So I would say 3 of them are all easy to figure out, and 1 is not. So if we think about what's easy, this is pretty easy. Remember that tan and inverse tan are inverse functions, so they cancel each other out. So that whole expression just results in that argument of 1/4. Get this out of the way. The secant of 0, if you think about the unit circle, and the angle 0, the point at that angle 0 is 1 theta, where secant is 1 over the cosine, and so if I take 1 over 1, I just get 1. So that's easy to do. Same thing if I'm finding the tangent of that same angle, I need to take sine and divide it by cosine, which is going to give me 0. So that entire second natural log term becomes the natural log of 1 plus 0, which is 1. Remember that the natural log of 1 equals 0. So that whole term is actually gone. So the only other thing we need to figure out here is, well, what is the secant of the inverse tan of 1/4? This takes a little bit of thinking, and I'm going to use a triangle to help you visualize what's happening. When we're evaluating expressions, we should start with the inside and work our way out. If we take the inverse tan of some ratio, it's going to produce an angle theta, where the ratio of opposite and adjacent sides are 1 over 4, or 1 to 4. I could use the Pythagorean theorem to solve for the hypotenuse. If I do 4 squared plus 1 squared, that hypotenuse becomes the square root of 17. So now, what I want to do is I want to find the secant of that same angle that was produced by this inverse tangent expression. So going to this triangle, think of what the secant ratio would be. So that's 1 over cosine, or in other words, the reciprocal of cosine. So hypotenuse over adjacent. And through all of that, we've determined that the square root of 17 over 4 is the expression for secant of inverse tangent of 1/4. And then 1/4 was the expression that we got here. This all canceled out to be 0. And therefore, this is our final answer. Obviously, it is acceptable to go ahead and write this as one fraction. You don't have to. I'm not sure exactly how picky MyMathLab will be. But the other thing to remember is that the absolute value is no longer necessary either, because this is a positive value.